Welcome to Chapter 21, where we will be talking about nuclear chemistry. To get into this, we're going to go back to some of the very beginnings of chemistry and talk about atomic structure. So we know that atoms are not just hard spheres. We have a small dense center, that is the nucleus, right? All the mass and the volume, and then the electron cloud is around it. So that's all the space around the nucleus, all the volume, none of the mass. And when it comes to characterizing atoms, what we care about are the numbers of subatomic particles. We have our protons, neutrons, electrons that we know about, and each different atom just has different numbers of all of the subatomic particles. And any two atoms have the same number for each type of subatomic particles, say 10 protons, 10 neutrons, 10 electrons. They're all going to have the exact same properties. And if you change those numbers of particles, you're going to change the properties of the atom. And so this overall structure, the nucleus, when we say it's this small dense center, it really is really small. Atoms we know are very small, and a nucleus is the tiniest little pinpoint of the middle of that atom. So the atom is kind of a big sphere, or that's a sphere, and then the smallest, very little middle of it is where your nucleus lies. So this idea that it really is none of the volume and all of the mass of the atom. And so each nucleus is composed of two different types of particles. You have protons that are positively charged and neutrons that are neutral. They have no charge. The mass of those particles is very small, right? 10 to the negative 24 grams. Atoms are tiny. So what we use is we call these 1 AMU, meaning an atomic mass unit. And the mass of a proton is about the same as the mass of a neutron, and they're both about one atomic mass unit. We're not going to use grams here because it's not very useful. We're going to use these atomic mass units, and basically it's similar to, not exactly the same, but it's similar to us just counting in a nucleus how many protons plus how many electrons. Number of protons plus number of electrons, because each of them is about 1 AMU. So then your other subatomic particle are the electrons, and the electrons are moving around the outside of the atom. They are not contained in the nucleus. And so this means they're on the outside of atoms. And so if two atoms are going to interact with each other, it's mediated by electrons. So chemistry is driven by electrons, right? All of the forming bonds, in redox chemistry, you're literally moving electrons between atoms. If you're forming bonds, breaking bonds, forming new bonds in acid-base chemistry, all of that is based around electrons. When you're talking about stabilities of enthalpy changes, that's all based on what is the most stable arrangement of electrons around different atoms. And so that's why we've really just forgotten about nuclei. We don't really care about nuclei because they are really in that dense center. This diagram right here is a way exaggeration to just to make this nuclei visible, but it really is the small dense core in the middle of an atom. And so if two atoms are going to interact, it is going to be by electrons. The nuclei do not interact because they don't physically touch each other, and they never will because all the electrons just get in the way. So that's why we really care primarily about electrons when it comes to doing chemistry, but the nuclei do have some dynamic natures, and they do have some things that we want to turn back to think about what nuclei, what kind of drives nuclei, and how they can change and what implications there are for that. So if we want to classify a nucleus, we know that really what it comes down to is how many protons and how many electrons are in there. You have to have integer numbers of each of those, and whatever the numbers of those is going to drive all of the properties of the nucleus. So the atomic number, which we usually represent that with a capital Z, is the number of protons in the nucleus. This does correspond to the charge on the nucleus because your neutrons are neutral. Each proton is +1, so the total number of protons is the total positive charge of the nucleus. The atomic number, that sort of high-class name, is given because that determines the name of the atom, the type of the atom. So whatever, we have that sort of translation on the periodic table, 14 protons, we call all of those silicon. So any atom that has 14 protons, we call it silicon. 6 is carbon, 9 is fluorine. We have all 20 calcium. We have these names that correspond with numbers of protons. So that's our primary one property, which is atomic number, which does correspond to charge. That's a common property of looking at things. And then atomic mass, which normally has the symbol A. Atomic mass is also called mass number, and I'm going to call it mass number. Technically, atomic mass is maybe a bit more preferred, but I'm going to refer to it as mass number a bunch because that's just what I've used. But that is the number of protons plus the number of neutrons. And so this would correspond to the total number of particles in the nucleus, right? The total number of things that are hanging around in your nucleus that have a mass. We normally would care about the number of neutrons because we say that is, kind of one of the properties we care about that determines it. But really, more frequently, we just talk about the total atomic mass or mass number of the nucleus because we really care about the properties of the nucleus. And the neutrons only contribute to that overall mass with the protons. You can figure out the number of neutrons just by subtracting protons from mass number because everything that's left has to be a neutron. So you can figure that out, and we'll use that information. When you're talking about nuclei, you really care about the charge, which is the atomic number, and the total mass of protons plus neutrons. And so we know that any given nucleus can have protons and neutrons in it. And so once we have a number of protons, that determines the name of that element, carbon, silicon, whatever it is. But you can have what are called isotopes. That's when you have atoms with the same number of protons. So that would be, for example, 6 protons is carbon. And so once you have that number of protons locked in, you've locked in the name, but you can have different numbers of neutrons, which means the overall mass in the atom can be dynamic. And so you can have different isotopes where you have the same number of protons, but different number of neutrons. And these would be then kind of different versions of that same type of atom. So for example, carbon, you're always going to have 6 protons, but you can have 6 or 7 or 8 neutrons or other different possibilities. And so for the most part, we haven't really talked too much about isotopes previously because they don't really matter as far as chemistry goes. The chemistry of an atom is determined by the electrons. The number of electrons for neutral is determined by the number of protons. So all these different isotopes have the same number and types of electrons. So they'll have the same chemical properties. So as far as we're concerned, they've all been the same. But they do have some other unique properties. We'll see there's some ramifications. So isotopes, the language of isotopes, when you say isotopes, you're talking about different versions. So a specific version of an element or an atom is called a nuclide. So a nuclide is a particular version of a nucleus, right? So nucleus, you have all sorts of different types of nuclei. A nuclide is then something where you have a particular version of an atom with a certain number of protons and a certain number of neutrons. So these carbons, for example, are going to be named based off the word carbon, which corresponds to the number of protons, and then a number for that mass number, for that sum of protons plus neutrons. So carbon 12 would then be that 12 corresponds to the sum of the 12 protons and the 12 neutrons. The 13 corresponds to this sum of 6 and 7, and carbon 14 corresponds to this sum of 6 and 8. And so these summations are always in there. So you'll note there's no explicit description of the neutrons, but you could back it out, right? Because 13 minus 6 would give you the 7 neutrons that are in carbon 13, for example. All right, so oftentimes we use nuclear symbols to describe a particular nuclide, right? We know that the element symbol just means, carbon just tells you that it has 6 protons in it. So we'd use a capital letter C. But we also want to describe what's in the what we can be more explicit about what's in the nucleus. These are also oftentimes called isotope symbols. And I will note people kind of just in language use isotope to mean nuclide. And I may slip into that every now and then. But generally, we do the correct terminology is going to be nuclide for this. So carbon 14 is our version. So if we have the symbol here, we can see carbon 14 is described. We have the element symbol, makes sense, we keep the carbon. Then the atomic number goes down on the bottom. And then the mass number, that is the sum of protons and neutrons, goes up on the top, the superscript. Those numbers always go before the symbol, right? After the symbol is where we put charge and number of atoms in a molecule. So numbers before the symbol correspond to nuclear information. And so all of this information in these nuclear symbols tell you everything about the nucleus. Really, the only thing there's to know about a nucleus is the number of protons and the number of neutrons, and all of that information is contained in here. You will note that if you look or poke around, the book also does sometimes get a little lazy. You don't always have the atomic number included. So for this case, what that would look like is it would just be 14C. You wouldn't include the 6. It would just be a blank space right here. you just leave it as a blank space. And the reason is that that atomic number 6 is already demonstrated by calling it carbon. So I'm going to generally always include that atomic number, or that atomic number. But if you kind of poke around, if you start watching some videos, or the book sometimes gets a little loosey-goosey with dropping those atomic numbers because it is redundant with the carbon. I'm going to do it just to be informative. This is educational. If you start poking around, especially in physics literature, they tend to just drop those numbers down the bottom, the atomic numbers. All right, first video down. Got a relatively light week because of the test. So just the participation for 17 going to be due on Friday. Week 13 homework due Saturday, and then the lab group 3 evaluation due Sunday over on Blackboard. That'll be our final group evaluation. And then don't forget, next week we've got the lab technique presentation, which will be going there. If you have any questions about anything, don't hesitate to reach out. Otherwise, we're just getting started. I think chapter 21 is a pretty fun one. You know, kind of cool, different, very different from a lot of the other stuff we've been talking about. If you have any questions, let me know. Otherwise, see you in the next video. Bye-bye.